97%. That's how much of Earth's primary stabilization system has collapsed since 2021. For over a century, something called the Chandler Wobble has kept our planet's spin steady, absorbing every gravitational tug, every shift in mass, every disturbance that could knock us off balance. It was our shock absorber, our gyroscope, and now it's gone. Just vanished. Without it, Earth isn't wobbling smoothly anymore. It's lurching, step by step, towards something we don't understand. The magnetic field is fracturing. Massive structures in the mantle are pulling the pole off course. And if the pattern holds, we're in the final stage of a cycle that repeats every 12,000 years. Stay with me until the end, because what I'm about to show you will change how you think about the ground beneath your feet. Subscribe and follow along, because as Earth searches for its new balance point, what we learn will determine whether we actually knew how our planet stays oriented in space, or overlooked something essential about the machinery keeping us stable, a wobble that's been silently compensating for every disturbance since the last ice age ended. There's a number that's been sitting in a database in Paris for the past 3 years, and almost nobody outside a very small circle of geophysicists has talked about it publicly. The number is 97%, and what it represents is the near total collapse of one of Earth's primary stabilization mechanisms. You've probably never heard of the International Earth Rotation and Reference Systems Service. Most people haven't. It sounds like the kind of bureaucratic organization that tracks minor adjustments to time zones or decides where to put GPS satellites. But the IERS does something far more fundamental than that. They measure where Earth actually is in space. Not where it's supposed to be according to theory, where it actually is right now at this exact moment. Every day, the IERS publishes what they call Earth Orientation Parameters. These are measurements that tell us precisely how our planet is oriented relative to the fixed stars, how fast it's spinning, and whether that spin axis is moving. You might assume we wouldn't need to measure this. You might think that once you calculate how a planet should spin, that's the end of the story. But Earth doesn't spin the way a perfect sphere in a physics textbook spins. It wobbles. It drifts. It responds to the gravitational pull of the moon and the sun and the redistribution of mass across its surface and inside its interior. The IERS tracks all of this, down to the millisecond, down to the centimeter. And in their data, something has gone catastrophically wrong. For more than a century, scientists have known about something called the Chandler Wobble. It's named after Seth Carlo Chandler, who discovered it in 1891 while analyzing star positions. The Chandler Wobble is a small circular motion that Earth's rotational axis makes, completing one loop roughly every 433 days. Think of it like the way a spinning top doesn't just spin straight up and down, but traces out a tiny circle as it rotates. The wobble itself is only about 3 to 6 meters in radius at the pole. You wouldn't notice it. You wouldn't feel it. But it's always been there. Here's what most textbooks won't tell you. The Chandler Wobble isn't just some quirky astronomical curiosity. It's a stabilizer. It acts like a shock absorber for Earth's rotational system, a way for the planet to dissipate excess angular momentum without lurching into a new orientation. When mass shifts on Earth's surface, when glaciers melt, or oceans slosh, or atmospheric pressure patterns change, these events tug on the planet's rotation. The Chandler Wobble absorbs these tugs. It damps them out. It keeps the system stable over long timescales, or at least it used to. The amplitude of the Chandler Wobble has been declining for decades, but around 2021, something changed. The signal didn't just weaken, it collapsed. By 2023, the oscillation that had persisted for at least a century, and probably for thousands of years before we started measuring it, had lost 97% of its energy. For all practical purposes, the Chandler Wobble is gone. Let me be very clear about what this does and does not mean. Earth has not stopped spinning. The planet has not tilted over on its side. We are not suddenly going to experience 6-month-long days and nights. This is not that kind of catastrophe. But it is a functional failure of a stabilizing mechanism that we didn't fully understand in the first place. And when a stabilizer disappears, the question becomes, what is now governing the system it used to protect? Scientists are very careful with their language. You will not find the word failure in any official IERS bulletin. You will not find the word collapse in peer-reviewed papers, at least not without heavy qualification. What you'll find instead are phrases like reduction in excitation, or diminished amplitude, or transition to a different dynamical regime. This is not cowardice. This is precision. But precision can obscure urgency. And right now, there is something urgent happening that most of the world doesn't know about. The disappearance of a stabilizing signal is, in some ways, more alarming than a sudden spike. If you see a spike, you look for a cause. You investigate what happened. But when something goes quiet, when a signal you've relied on simply fades away, it means the system has shifted into a state where that signal is no longer necessary or no longer possible. It means the rules have changed. Think of it this way. Imagine you're driving a car with shock absorbers. The shock absorbers smooth out the bumps in the road. You don't think about them. You don't notice them working. But one day, you're driving along, and you realize the ride is different. Not rougher at first, just different. You take the car in, and the mechanic tells you the shock absorbers have failed completely. But here's the strange part. The car isn't bouncing wildly. It's just rigid. And that rigidity, you realize, means every bump in the road is now going straight into the frame. The car is absorbing nothing. It's reacting to everything. That's where Earth is right now. If the Chandler wobble is gone, and the planet is still spinning, still maintaining its axis, then something else must be providing stability. Or something else is about to stop providing it. And the question nobody wants to ask out loud is this. What happens when the thing that takes over is less stable than what we lost? We're about to find out. Because Earth's rotational axis isn't staying still. It's moving. And it's not moving smoothly. You've probably seen a figure skater pull in their arms during a spin. They speed up. They extend their arms. They slow down. This is conservation of angular momentum, and it's one of the most fundamental principles in physics. A rotating object will keep rotating at a constant rate unless something changes its distribution of mass or applies an external force. Earth is no different. It's a spinning object, and like any spinning object, it wants to settle into an equilibrium. But here's the thing about equilibrium. Equilibrium is not the same as stability. A ball sitting at the bottom of a bowl is in stable equilibrium. If you nudge it, it rolls back to the center. A ball balanced on top of a dome is in unstable equilibrium. If you nudge it even slightly, it rolls off and never comes back. A ball rolling around the inside of a bowl is in dynamic equilibrium. It's constantly moving, but it's moving in a predictable pattern. The question we have to ask about Earth is, which kind of equilibrium is our planet in right now? For the past century, the assumption has been that Earth's rotational axis is in stable equilibrium, perturbed slightly by predictable forces like tides and atmospheric circulation, but always returning to a mean position. The Chandler wobble was part of that return mechanism. It was evidence that the system could absorb shocks and settle back down. But if the wobble is gone, then either we've moved into a new stable equilibrium, or we've moved into something else entirely. Recent data from the IERS suggests something troubling. Instead of a smooth, continuous precession of the pole, the motion looks increasingly episodic, step-like. The pole moves, then pauses, moves again, then pauses. These aren't massive jumps. We're talking about centimeters, maybe a few meters over the course of months. But the pattern is wrong. It doesn't match the smooth, sinusoidal curves you'd expect from tidal forcing or seasonal mass redistribution. It looks, in the language of dynamical systems, like a series of corrections, like lurching. Now, lurching is a loaded word. It conjures images of catastrophic instability, of a planet wobbling out of control. That's not what's happening, at least not yet. But mathematically, lurching is a defensible description of what happens when a system can no longer make continuous corrections and instead adjusts in discrete steps. It's the difference between a thermostat that smoothly regulates temperature and one that lets the room get too hot, then blasts the air conditioning, then lets it get too hot again. Both systems maintain an average temperature, but one is smooth, the other is oscillatory. And the oscillatory system is always closer to breaking. So what's causing these step-like adjustments? The answer, in part, is tides. Not ocean tides, though those matter too. Gravitational tides. The moon and the sun pull on Earth constantly, creating bulges in the solid body of the planet, not just in the oceans. These tides exert torques on Earth's rotation, and under normal circumstances, those torques are small and continuous. The Chandler wobble used to damp them out, but now, without that damping mechanism, the tides are acting more directly on the planet's orientation. Tides don't create instability. They're predictable, but they do act as amplifiers. If the planet is already in a state of reduced stability, if it's already vulnerable to perturbation, then tidal forces that would normally be negligible can start to matter. They can tip a system that's on the edge, and the evidence suggests that's exactly what's happening. The timing of the pole's episodic movements correlates, loosely but noticeably, with periods of maximum tidal stress. Spring tides, perigee, syzygy. When the moon and sun align, when their gravitational pulls combine, the pole moves, and then it stops. But here's the unsettling part. The direction of these movements isn't random. It's not a chaotic wandering. The pole is drifting, slowly but persistently, toward a specific region of Earth's surface, and that suggests something even more troubling. It suggests that the equilibrium point itself, the place where Earth wants to balance, is moving. And if the equilibrium point is moving, then something inside the planet is redistributing mass in a way that's changing the gravitational landscape. Think about balancing a broom on your hand. If the broom is perfectly vertical, it balances. But if someone slowly ties a weight to one side of the broom, the balance point shifts. You have to move your hand to keep it upright. Earth is doing the same thing right now. Except we don't know what the weight is. We don't know where it's going, and we can't move our hand. From the surface, everything looks calm. The days are still 24 hours long. The seasons still change. The stars still rise and set in the same places. But underneath, the machinery that keeps all of this running smoothly is struggling. The planet is accumulating imbalance, and sooner or later, it's going to have to correct. The question is, what happens when it does? If you've been following climate science over the past few decades, you've probably heard the explanation for polar motion that goes something like this. Ice sheets are melting, water is redistributing from the poles to the equator, and this changes Earth's moment of inertia, which shifts the rotation axis. It's a neat story. It's intuitive, and it's probably wrong, or at least it's catastrophically incomplete. The numbers don't add up. Even the most extreme estimates of ice melt and ocean redistribution over the past century can account for, at most, a few centimeters of polar shift. We're seeing motions on the order of meters, with accelerations that suggest much larger shifts are coming. Surface mass redistribution is real, and it does matter, but it's not the primary driver of what's happening right now. So if it's not the surface, then it has to be something underneath. Something in the mantle. The mantle is not uniform. This is one of the most important and least understood facts about Earth's interior. When you picture the mantle, you might imagine a smooth layer of hot rock, convecting slowly like honey on a stove. But the reality is far more complex. The mantle is full of heterogeneities, regions where the density and temperature and composition vary dramatically. And some of these heterogeneities are enormous. At the base of the mantle, just above the outer core, there are two massive structures that geophysicists call large low-shear velocity provinces. The name is technical, but the concept is simple. These are continent-sized blobs of anomalous material, each thousands of kilometers across and hundreds of kilometers tall, sitting beneath Africa and the Pacific Ocean. Seismic waves slow down when they pass through these regions, which suggests the material is either hotter or compositionally different from the surrounding mantle. Or both. Nobody knows exactly what these structures are. They might be ancient remnants of subducted ocean crust that have accumulated at the core mantle boundary over billions of years. They might be primordial material left over from Earth's formation. They might be actively forming right now, fed by plumes rising from the outer core. But whatever they are, they represent massive concentrations of mass in the deep interior. And mass, in a rotating system, exerts gravitational influence. Here's where things get interesting. If you have a rotating sphere, and you place a mass asymmetrically inside it, the sphere will try to reorient itself so that the mass ends up along the rotation axis. This is called the polar wander effect, and it's been observed on other planets. Mars, for example, has a massive volcanic province called Tharsis, and the entire planet appears to have reoriented itself so that Tharsis ended up on the equator. The same principle applies to Earth. If the mantle has large-scale mass anomalies, the planet will slowly shift its rotation to accommodate them. This isn't speculation. There's evidence in the paleomagnetic record that suggests Earth's poles have wandered significantly over geological time, not because the magnetic field reversed, but because the entire solid body of the planet rotated relative to the core. It's called true polar wander, and it's one of the most dramatic processes a planet can undergo. The continents don't move. The mantle doesn't convect any differently. But the whole planet tips over, sometimes by tens of degrees, to bring itself back into balance. And here's the kicker. The timescale for true polar wander is long, millions of years usually. But if the mantle is undergoing a rapid reorganization, if those massive structures at the base are moving or growing or collapsing, then the timescale could shorten dramatically. Thousands of years, hundreds of years, maybe less. The evidence for directional bias in polar motion is subtle, but real. Over the past 2 decades, the pole has been moving consistently toward a region centered roughly around the Pacific, not wandering randomly as you'd expect from surface mass redistribution. Moving, as if it's being pulled, and the only thing with enough gravitational muscle to pull the entire rotational axis of a planet is something massive, something deep, and something that's changing. This is where scientific consensus fractures. Some researchers argue that the mantle is essentially static on human timescales, that any mass redistribution is too slow to matter. Others point to evidence of rapid mantle plumes, of sudden slab avalanches in subduction zones, of catastrophic reorganizations that happen on timescales of centuries, not epochs. The data is ambiguous. The models disagree. But the one thing everyone agrees on is that if the mantle is exerting control over polar motion, then surface processes are irrelevant. We could stop all ice melt tomorrow, and the pole would keep moving. Because what's happening now isn't being driven by us. It's being driven by forces that were set in motion long before humans existed. Forces that operate on timescales that make civilizations look like mayflies. And those forces, whatever they are, don't care about climate treaties or emission targets or any of the things we think we can control. So the question becomes, if the mantle is the engine, what's fueling it? What's happening even deeper in the churning metallic sea at the center of the planet that could be reorganizing thousands of kilometers of solid rock? You've probably seen the headlines. Earth's magnetic field is weakening. Magnetic pole reversal imminent. Are we losing our cosmic shield? These stories pop up every few years, usually accompanied by dramatic graphics showing field lines collapsing or the poles flipping overnight. And they're not entirely wrong. The field is weakening. The poles are moving. But the real story is far stranger than the headlines suggest. The issue isn't field strength. Not primarily. The issue is geometry. Earth's magnetic field is generated by the motion of liquid iron in the outer core, a process called the Geodynamo. Think of it like a self-sustaining dynamo, where the movement of electrically conductive fluid generates a magnetic field, and that magnetic field, in turn, organizes the flow of the fluid. It's a feedback loop, and under normal circumstances, it's incredibly stable. The field has existed, in some form, for at least 3.5 billion years. It survived asteroid impacts, supervolcano eruptions, ice ages, continental breakups. It's one of the most robust features of our planet. But robustness doesn't mean uniformity. The field is not a smooth dipole, like the field around a bar magnet. It's lumpy, asymmetric, full of local anomalies and patches where the field strength varies by a factor of 2 or more. And over the past few decades, those anomalies have been growing. The most famous of these is the South Atlantic anomaly, a region stretching from South America to Southern Africa, where the magnetic field is significantly weaker than average. Satellites passing through this region experience higher radiation doses. Astronauts on the International Space Station see flashes of light when the station crosses it, caused by high-energy particles hitting their retinas. The anomaly has been there for decades, but it's been expanding, and more importantly, it's been moving westward at a rate of several kilometers per year. Now, movement in the magnetic field is normal. The field drifts. It fluctuates. But what's happening in the South Atlantic anomaly is different. It's not just drifting, it's fragmenting. Recent satellite data shows that the anomaly is splitting into 2 separate lobes, as if the underlying structure of the field in that region is reorganizing itself. And this is where things get complicated, because the surface manifestation of the field, the thing we can measure with satellites and ground-based magnetometers, is only a reflection of what's happening deep in the core. And what's happening in the core is hidden from us. We know the outer core is in constant motion. We know there are flows and eddies and jets of liquid iron moving at speeds of kilometers per year. We know that these flows are influenced by the rotation of the planet, by the heat flux from the inner core, by the gravitational pull of the moon and the sun. But we can't see them directly. We can only infer their existence from the changes they produce in the magnetic field. And right now, those changes are accelerating. There's a debate in the geophysics community about whether the inner core, the solid ball of iron at the very center of the planet, is rotating at the same speed as the rest of the Earth. Some studies suggest it's rotating slightly faster, maybe 1/10 of a degree per year ahead of the mantle. Others suggest it's slowing down. Still, others suggest it's stopped entirely relative to the surface, or even reversed. The data is contradictory. The models don't agree, but the fact that we're even having this debate is significant, because if the inner core's rotation is changing, then the coupling between the inner core, the outer core, and the mantle is changing. And that coupling is what keeps the geodynamo stable. Here's a speculative idea, but one worth considering. What if the mechanical rotation of the deep interior is changing faster than the magnetic field can respond? The geodynamo is electromagnetic, but it's also mechanical. It depends on flows, on convection, on rotation. If the rotation rate of the inner core shifts, the flow patterns in the outer core have to adjust. But magnetic fields don't adjust instantaneously. They have inertia. They diffuse slowly through conducting material. So you could have a situation where the mechanical system has already moved into a new state, but the magnetic field is still catching up. And during that transition, the field would look chaotic, fragmented, decoupling. This is not the same as a magnetic reversal. Reversals happen when the dipole field collapses entirely and rebuilds in the opposite direction. We've had hundreds of reversals over Earth's history, and as far as we can tell, they didn't cause mass extinctions or catastrophic climate shifts. But what we're seeing now doesn't look like the beginning of a reversal. It looks like something else, a reorganization, a decoupling of the field from the rotation of the solid Earth. And we don't have good records of what that looks like, because we've only been measuring the field in detail for a few hundred years. The paleomagnetic record, locked in ancient rocks, shows that the field has done strange things in the past. There are periods of rapid change, excursions where the poles wandered far from the geographic poles and then snapped back. There are periods of low intensity, where the field weakened but didn't reverse. But the resolution of the paleomagnetic record is coarse. We can't see the details. We can't see the month-to-month or year-to-year changes. We can only see the average over centuries or millennia. And that means we don't know if what's happening now is unprecedented, or if it's happened many times before, and we just didn't notice. But here's the thing. If the magnetic field is reorganizing, and the inner core is changing its rotation, and the mantle is redistributing mass, then these aren't independent processes. They're coupled. They feed back on each other. A change in the core affects the mantle. A change in the mantle affects the rotation. A change in the rotation affects the core. It's a system. And systems, especially complex nonlinear systems, have a habit of transitioning suddenly from one state to another. The question is, are we watching chaos, or are we watching the early stages of a transition that follows a pattern that Earth has followed before? Every 12,000 years or so, something happens. Or at least, that's the claim. You'll find it in fringe science books, in YouTube videos with dramatic music, in corners of the internet where ancient catastrophe theories thrive. And you'll find it, more quietly, in legitimate paleoclimate research, in ice core data, in marine sediment records, the 12,000-year cycle. The problem is, nobody agrees on what it means. Let's start with what we actually know. Roughly 12,800 years ago, something dramatic happened to Earth's climate. The planet had been warming, coming out of the last ice age, and then suddenly, over the course of just a few decades, it plunged back into near glacial conditions. This event is called the Younger Dryas, and it lasted for about 1,000 years before the warming resumed. The cause is still debated. Some researchers point to a massive influx of fresh water from melting ice sheets disrupting ocean circulation. Others suggest a cosmic impact, maybe a comet or asteroid airburst that triggered wildfires and atmospheric cooling. The evidence is messy, but the event itself is real. Go back another 12,000 years or so, to around 24,000 years ago, and you find another major climate transition. This is the last glacial maximum, the peak of the last ice age, when ice sheets covered much of North America and Europe. Go back another 12,000 years, and you're in an interglacial period, warm and stable. Back another 12,000, and you're in another glacial period. The pattern isn't perfect. The timing varies by a few thousand years, depending on which proxy records you use. But there's a rhythm there, a quasi-periodicity. Now, climate cycles are real. We know about Milankovitch cycles, the variations in Earth's orbit and axial tilt that drive ice age rhythms on timescales of 20,000 to 100,000 years. But Milankovitch cycles are smooth and predictable. They don't explain sudden transitions. They don't explain events like the Younger Dryas, where the climate flipped in a matter of decades. and they especially don't explain why some of these transitions seem to cluster around a 12,000-year interval. Enter the paleomagnetic record. When you look at the intensity of Earth's magnetic field over the past 100,000 years, reconstructed from volcanic rocks and sediment cores, you see variability. Lots of it. The field's strength goes up and down. Sometimes it's twice as strong as it is today. Sometimes it's half as strong. And buried in that variability are brief periods, lasting a few centuries to a few millennia, where the field weakens dramatically and the poles wander far from their usual positions. These are called geomagnetic excursions. They're not full reversals, but they're significant perturbations. And here's where things get interesting. Some of these excursions seem to correlate with abrupt climate events. The Lachamp excursion, around 41,000 years ago, corresponds with a period of rapid climate change and increased cosmic ray bombardment. The Mono Lake excursion, around 34,000 years ago, same thing. The timing isn't perfect, but it's suggestive. And when you plot these excursions on a timeline, some researchers claim to see a pattern, a 12,000-year pattern. Now, I need to be very clear here. This is not settled science. The dating of these events is uncertain, often with error bars of plus or minus a few thousand years. The causal link between magnetic excursions and climate change is speculative at best, and the idea that there's a strict 12,000-year periodicity is almost certainly an overfitting of noisy data. Humans are pattern-seeking animals. We see cycles everywhere, even in random noise, especially in random noise. But rejecting all patterns is also dangerous, because Earth is not a random system. It's a deterministic system with feedback loops, resonances, and threshold behaviors. And deterministic systems, even chaotic ones, can exhibit quasi-periodic behavior. Not like a clock, where every tick is exactly the same, but like a metastable system, where the same set of initial conditions tends to produce the same kind of outcome, even if the timing varies. Think of it this way. Imagine a ball sitting in a bowl, but the bowl is on a table that's slowly tilting. Most of the time, the ball just sits there. But eventually, the tilt reaches a critical angle, and the ball rolls out. If you reset the system and tilt the table again, the ball will roll out at roughly the same angle. Not exactly the same, because there's randomness in the system, but roughly. That's a threshold behavior, and Earth's climate, Earth's magnetic field, Earth's rotation, they're all full of thresholds. The mantle convects, the core churns, ice sheets grow and collapse, ocean currents shift. These processes happen on different timescales, but they interact. And when you have multiple interacting processes, each with its own resonance, you can get beat frequencies. You can get quasi-periodic oscillations that emerge from the interaction of non-periodic components. It's called mode locking, and it shows up everywhere in physics, from pendulums to planetary orbits to the orbits of galaxies. So maybe there is a 12,000-year rhythm, not because Earth is following a cosmic clock, but because the interaction of the core, the mantle, the crust, the oceans, and the atmosphere naturally produces a recurrence interval on that timescale. Or maybe the pattern is an illusion, a trick of statistics and wishful thinking. The honest answer is, we don't know. But here's what we do know. The magnetic field is changing. The rotation is changing. The climate is changing. And these changes are happening simultaneously. Whether they're connected by a 12,000-year cycle or by something else entirely, the fact remains. Earth's major systems are in transition. And transitions, by their nature, are unpredictable. Which brings us to a more unsettling question. If Earth isn't the only thing in transition right now, if there are other systems, other scales that are also showing signs of instability, then maybe the problem isn't just Earth. Maybe the problem is that we're reaching the limits of our ability to predict anything at all. On January 16th, 2025, a team of astronomers announced the discovery of an exoplanet. This is not unusual. We discover exoplanets all the time now, thousands of them. The count passed 5,000 a few years ago and keeps climbing. Every week, it seems, there's a new paper describing another world orbiting another star. Rocky planets, gas giants, super-Earths, hot Jupiters. The catalog grows so fast that individual discoveries barely make headlines anymore, unless there's something truly exceptional. A planet in the habitable zone. A planet with an atmosphere we can characterize. A planet that might, just might, harbor life. But this one was different. Not because of what it was, but because of when we found it. Because the signal for this planet had been sitting in archival data for more than a decade. It was there the whole time. Clear, measurable. Repeating like clockwork every 47 days. We just didn't see it. The planet orbits a star about 400 light years away. Nothing particularly special about it. Not unusually bright. Not unusually close. Just another yellow dwarf star among billions in our galaxy. The discovery came from a reanalysis of data from the Kepler Space Telescope, the mission that revolutionized exoplanet science by staring at a single patch of sky for years, watching for the tiny dips in starlight that occur when a planet passes in front of its host star. Kepler operated from 2009 until 2018, when it finally ran out of fuel and was retired. But the data it collected, 4 years of continuous observations of over 150,000 stars, is still being analyzed, still yielding discoveries. A researcher digging through old light curves noticed a pattern that had been flagged by automated algorithms years ago but dismissed as noise. The software had seen it. The computer had registered the periodic dimming. But somewhere in the processing pipeline, a decision had been made. The signal didn't match the template closely enough. The probability score was too low. The flag was categorized as a false positive and moved into a discard pile that nobody had bothered to check manually. It wasn't noise. It was a planet. A Neptune-sized world, about 4 times the diameter of Earth, transiting its star every 47 days. The signal was clear, once you knew what to look for. The dips in brightness were consistent. The timing was regular. The depth matched what you'd expect from a planet of that size. There was no ambiguity, no need for exotic explanations or statistical gymnastics. It was just sitting there, in the data, waiting. But for 10 years, nobody looked. Why does this matter? Why should we care about one more exoplanet in a catalog of thousands, especially one that's unremarkable in almost every way? Because it tells us something profoundly uncomfortable about the limits of our detection systems, about the gap between data and understanding, about the difference between collecting information and actually seeing what it means. Automated algorithms are incredibly good at finding patterns in data. They have to be. The volume of information we collect now is staggering. Kepler alone generated over 2 petabytes of data during its mission. That's 2 million gigabytes. No human could possibly examine all of it manually. So we build software to do it for us. We train neural networks. We write pattern-matching code. We set thresholds and criteria and let the computer sift through millions of light curves and flag potential planets in seconds. And it works. Most of the time. The algorithms are responsible for the vast majority of exoplanet discoveries. They're faster than humans, more consistent. They don't get tired. They don't get distracted. They don't have bad days where they miss something obvious because they're thinking about lunch. But they're also incredibly literal. They do exactly what they're programmed to do. Nothing more, nothing less. If a signal doesn't match their training set, if it doesn't look exactly like the kind of planet we've already found, the algorithm ignores it. Or worse, it flags it as anomalous and moves on. And humans, even expert astronomers who should know better, trust the algorithms. We trust them because we have to. Because there's too much data to check manually. because the algorithms have been right so many times before. We assume that if the software didn't flag it as important, it probably isn't. This planet wasn't hidden by some exotic physics. It wasn't obscured by a dust cloud, or drowned out by stellar variability, or masked by the gravitational influence of other planets in the system. There was no astrophysical reason we should have missed it. It was just unremarkable, right on the edge of what the algorithms were tuned to detect. The transit depth was a little shallower than the typical Neptune. The orbital period was a little longer than the sweet spot where Kepler was most sensitive. The signal-to-noise ratio was good, but not great. It fell into a gray area where the software had to make a judgment call, and the software called it noise. And so it sat, unnoticed, in a database that thousands of researchers had access to for an entire decade. Graduate students working on theses, postdocs hunting for unusual systems, citizen scientists combing through the data as part of crowdsourced analysis projects. Any one of them could have found it, but none of them did, because they were all using the same algorithms, the same filtering criteria, the same automated pipelines, and those tools all made the same decision: not interesting enough to warrant human attention. Now, this discovery has nothing to do with Earth's rotation or its magnetic field or any of the things we've been talking about, at least not physically. The exoplanet doesn't exert gravitational influence on us. It's 400 light-years away. That's 2 quadrillion miles. Its existence doesn't affect our geodynamo. It's not sending signals that perturb our orbit or tug on our tides. This is not some cosmic conspiracy where distant planets are secretly controlling Earth's behavior. That would be absurd. But psychologically, it's devastating, because it forces us to ask a question we'd rather not think about. What else are we missing? We have sensors everywhere. Satellites orbiting Earth, measuring everything from sea level to ice thickness to magnetic field strength. The Swarm constellation tracking variations in the geomagnetic field. Grace satellites measuring changes in Earth's gravitational field caused by mass redistribution. Radar altimeters monitoring ocean heights down to the centimeter. Ground-based observatories tracking seismic waves, cosmic rays, atmospheric composition, solar wind. GPS networks measuring the positions of continents as they drift. Tide gauges, weather stations, magnetometers, gravimeters, an entire global infrastructure dedicated to monitoring every aspect of our planet's behavior. Data streaming in constantly, terabytes per day, more than any human could ever analyze. And we trust that our algorithms, our pattern-matching software, our automated alert systems will notify us if something important happens. We trust that if there's a significant change, if something deviates from the expected baseline, the software will flag it. It will send an email. It will trigger a warning. Someone will notice. But what if the important thing doesn't look like what we expect? What if it's right there in the data, clear as day, once you know to look for it, but nobody's looking because the algorithms dismissed it as uninteresting? What if the signal of Earth's destabilization is sitting in an IERS database right now, flagged years ago as statistical noise, waiting for someone to take a second look? The timing of this exoplanet discovery, coming in the same month that the Chandler Wobble data is becoming more widely discussed, is coincidental. There's no causal link, no shared mechanism. But coincidence doesn't mean irrelevant, because the lesson is the same. The warning is the same. Late realization is not the same as no realization, but it's almost as dangerous. Maybe more dangerous in some ways, because late realization creates the illusion that we're paying attention, that we would have noticed sooner if it were really important. If you discover a problem 10 years after it started, you've lost 10 years of lead time. 10 years you could have spent understanding the mechanism, building models, preparing responses. 10 years of data that could have shown you the trajectory, the acceleration, the point of no return. And if the problem is one that develops slowly at first and then accelerates, if it's the kind of process that spends decades in a quasi-stable state before tipping suddenly into runaway change, those 10 years might be the difference between manageable and catastrophic. Earth system monitoring is not as robust as we like to think. The IERS tracks rotation, but they're chronically underfunded. Their budget is a rounding error compared to what we spend on space telescopes or particle accelerators. Magnetic field satellites have gaps in coverage. SWARM is a constellation of 3 satellites, but 3 satellites can't give you continuous global coverage. There are always blind spots. Seismic networks are denser in wealthy countries than in poor ones. If a major geological event happens in a remote region, we might not detect it until days or weeks later, if at all. And all of this data from all of these sensors is analyzed by algorithms that were designed to detect known patterns, not unknown ones. We're very good at seeing what we expect to see. Seasonal variations in Earth's rotation, annual fluctuations in the magnetic field, seismic activity that fits established models of plate tectonics. These are the things our software is tuned to recognize. These are the patterns it's trained on. We're terrible at seeing the unexpected, at recognizing signals that don't fit the template, at noticing when the baseline itself is shifting. And here's the thing, the unexpected doesn't announce itself. It doesn't send a press release. It doesn't show up in bold red letters on a monitoring dashboard. It just sits there, in the data, quiet and patient, waiting for someone to notice, waiting for a researcher to get curious, to dig through the archives, to question an old classification, to wonder if maybe, just maybe, that thing we dismissed as noise 10 years ago was actually the first warning sign of something we should have been paying attention to all along. And by the time someone does notice, by the time someone pulls the signal out of the noise and realizes what they're looking at, it's often too late to do anything but watch. Too late to intervene. Too late to prepare. You can document the process. You can build better models for next time, but you can't stop what's already in motion. So the question becomes, if we're missing planets in archival data, if we're dismissing signals that don't fit our models, if our detection systems are blind to anything that doesn't look like what we've already seen, what are we missing about Earth? What signals are sitting in the IERS database right now, in magnetometer records, in seismic tomography, that haven't been flagged because they don't look like anything we've trained our systems to recognize? What patterns are there, clear and obvious once you know to look for them, that nobody's looking for because we don't even know they exist? And more importantly, what happens when we finally do recognize them? What happens when someone, 10 years from now, or 20, or 50, digs through the archives and finds the signal we're generating today? The signal that shows Earth's stabilization system collapsing in real time. The signal that marks the beginning of the transition. What will they think when they realize we had the data all along? That we could have known if only we'd looked? Will they wonder why we didn't see it? Or will they understand, with the bitter clarity of hindsight, that we were never really looking at all? Let's talk about prediction. Specifically, let's talk about why Earth systems are fundamentally hostile to it. You've probably heard the phrase, the butterfly effect. A butterfly flaps its wings in Brazil, and a month later, there's a tornado in Texas. It's a metaphor for sensitive dependence on initial conditions. The idea that tiny changes in a complex system can lead to wildly different outcomes. And it's true, to a point. But the real problem with predicting Earth systems isn't chaos. It's regime change. Chaos is predictable, in a weird way. A chaotic system is deterministic. If you know the exact state of the system at one moment, and you know the equations that govern it, you can predict what it will do. The problem is that you can never know the exact state. There's always measurement error. And in a chaotic system, that error grows exponentially. Weather is chaotic, which is why we can forecast 3 days out with reasonable accuracy, 7 days out with some accuracy, and beyond that, it's essentially noise. But we know it's chaotic. We know the limits. We build our models accordingly. Regime change is different. Regime change is when the rules themselves shift. When a system that's been behaving one way for decades or centuries suddenly starts behaving in a completely different way, governed by a completely different set of dynamics. And the thing about regime change is that it's invisible until it happens. Because your models are trained on the old regime, they're built to interpolate between known states, not to extrapolate into fundamentally new territory. Let me give you an example. Imagine you're trying to predict the flow of a river. For years, the river has been calm, flowing steadily within its banks. You build a model based on that behavior. You train it on historical data. The model gets very good at predicting next week's flow rate based on rainfall and snowmelt. And then, one spring, there's an unusually warm snap. The snowpack melts all at once. The river floods. Not just a bigger version of normal flow. A completely different behavior. The water jumps the banks, carves new channels, changes the landscape. Your model, trained on calm flow, has nothing to say about this. It fails catastrophically. This is what's happening with Earth systems right now. Climate models, rotation models, geomagnetic models. They're all trained on data from the past few decades or centuries. And for the most part, that data represents a stable regime. The Holocene, the interglacial period we've been in for the past 12,000 years or so, has been remarkably stable. Temperatures have varied. Ice sheets have grown and shrunk, but the basic dynamics have stayed the same. And so our models assume stability. They assume continuity. They assume that the future will look like the past, just with minor variations. But what if we're leaving the stable regime? What if the Chandler Wobble collapse, the magnetic field reorganization, the Mantle redistribution are all symptoms of Earth transitioning into a new dynamical state? A state we don't have historical data for because it hasn't existed in recorded history? This is where artificial intelligence makes things worse, not better. AI is incredibly good at pattern recognition. Feed it enough data, and it can find correlations, predict trends, extrapolate curves. But AI is fundamentally conservative. It's trained on the past. It learns what has happened, and it assumes that's what will happen. And the better the AI gets at modeling the old regime, the more confident it becomes, and the more catastrophically it fails when the regime changes. There's a concept in machine learning called distribution shift. It's when the data you're making predictions on comes from a different distribution than the data you trained on. And when that happens, your model's accuracy plummets. Imagine training a self-driving car in sunny California and then deploying it in a snowstorm in Minnesota. The car has never seen snow. It doesn't know how to interpret it. It crashes. Now, imagine training Earth system models on 12,000 years of Holocene stability and then deploying them in a period of rapid transition. They crash too, just more slowly and with higher stakes. The overconfidence problem is real. We see smooth graphs, precise error bars, confident projections, and we assume precision means accuracy. But precision just means your measurements agree with each other. Accuracy means they agree with reality. And when reality is changing in ways you haven't modeled, precision is meaningless. This is the philosophical tension we're stuck in. We know something is wrong. The data shows it. The Chandler Wobble is gone. The magnetic field is reorganizing. The pole is drifting. But we don't know what it means. We don't know if this is the beginning of a catastrophic transition or just a fluctuation that will settle down in a few decades. And our tools, the models and algorithms we've built to make sense of the world, are optimized for a world that no longer exists. So what do we do? How do you plan for something you can't predict? How do you prepare for regime change when you don't know what the new regime will look like? The honest answer is you can't. Not in the traditional sense. You can't build a model. You can't run a simulation. You can't calculate probabilities, because all of those tools assume you know the rules. And when the rules are changing, the only thing you can do is watch carefully, respond quickly, and accept that uncertainty is the new normal. Earth has been stable for a long time, long enough that we've built civilizations on the assumption that it will stay stable, long enough that we've forgotten what instability looks like. But stability is not a permanent state. It's a temporary equilibrium, maintained by forces that we don't fully understand and can't fully control. And when those forces shift, when the balance tips, the transition can be fast. Faster than we expect. Faster than we can adapt. So here's the question I'll leave you with. Not a rhetorical question, a real one. Is Earth losing its balance? Is the planet tipping into a new state, a new configuration, a new way of being that we've never seen before? Or are we losing our ability to recognize instability in time? Are we so accustomed to smooth futures, to predictable trends, to models that work, that we've become blind to the signs that the system is changing underneath us? Maybe it's both. Maybe Earth is changing, and we're failing to see it clearly because our tools are designed for a world that no longer exists. And if that's true, then the question isn't whether something catastrophic is coming. The question is whether we'll recognize it before it's too late.